Today we're going to be talking about rate of reaction, or at least getting the background to rate of reaction so that we actually know how to do the calculations, know what to expect, know the kinds of things we're going to be looking for. So we need to sort of remind ourselves about what it means that something is a rate. And if you're talking about a things, it's how fast they're going to be happening. So if you're talking about a heart rate, it's how many beats, how many events per minute. Usually. If you're talking about a rate of travel or a speed, that's going to be kilometers per hour. So I'm measuring something and over a certain amount of time. So when we talk about a reaction rate, for us in chemistry, it's going to be how much product is being produced, how fast it's being produced, so we have that time piece of it, or how fast a reactant is being consumed. Now, think about this in terms of what it is we are measuring. The time part is kind of obvious, but the other piece of it is, what am I going to be measuring and comparing? Well, in chemistry, the thing is usually going to be a concentration in moles per liter. So I would express the rate in some form like this, where it is the concentration, the change in the reactant, rather not the reaction, but change in the reactant over time, or perhaps a change in the product over time. And which one I pick is going to depend on a bunch of things. Now, just some notation stuff there, those square brackets around the R or the delta R or the delta P, that means the concentration. So it's the change in concentration over time. If concentration is in moles per liter and time is in seconds, and it's a moles per liter per second, which I can express in a couple of different ways. Now, it doesn't have to be a moles per liter per second. Some reactions, maybe it's moles per liter per minute or moles per liter per hour. Or if you were measuring a gas, maybe it's the volume that's being produced, and we're probably going to do one of those in class. So it doesn't have to be moles per liter per second, but that's typically the one that we're going to be using most often. It's also worthwhile to understand that a rate is not going to be constant over time, but the reaction is going to start out going a little bit quicker and slowing down as it gets close to being finished. Also, if you look at this graph, the red line is going to be the reactants, how they are changing. They're going to start fairly high, and then they're going to come down more quickly initially, and then they're going to slow down, whereas the products are going to start very low, and they're going to increase over time. Now, if you think about it in terms of reactant molecules that have to, I don't really want to say it this way, but find one another in order for a reaction to happen, as you get less and less reactant, more and more product, it's going to be more difficult for those reactant particles to find one another to make a reaction. So that's one of the reasons why it starts to tail off and to level off. The curve doesn't always have to be the same shape. So in this case, the reaction, as I mentioned, starts out going a certain rate. During the middle of it is going at a different rate, and near the end of it is going a different rate again. So just another way of looking at what I just got finished saying. Okay, now curves, if you think about math, we were almost always dealing, I shouldn't say we, you were almost always dealing with straight lines because they were easier to deal with because we could come up with the slope of a straight line. Curved lines are a little bit tricky. So what do we do with a curve? Two options. One, invent a straight line. We can just sort of compare the start point and finish point of somewhere of 2 points on that line. It doesn't have to be the exact start or the exact finish, just comparing 2 points on that line, 2 different times, concentrations at each one of those, and invent a straight line as a reasonable approximation of what we're trying to do. The other option is to draw a tangent to that line. Now, if you've ever tried doing that, tangents by hand are really, really tricky, but modern computer programs give us much better options for coming up with tangents to that line. But either way, when I'm dealing with a curve, I can't really deal with a curve. I need to be dealing with a straight line, and then I can find the slope. Bet you when you were in math, you were never, and you asked, when are we ever going to use this slope stuff? I bet you the teacher never said, well, in chemical rates of reaction. It might not have helped if they did, but now you know. Okay, now earlier I said you could use a reactant or a product, and does it matter which one you use? And the answer is it shouldn't matter because they're going to be related. And what I mean by that is if it's within one reaction, whether you're talking about the rate of this or the rate of that, the numbers could be different, but it shouldn't matter because they are going to be related. How many numbers are different? Well, if I take a look at this combustion reaction, and for the sake of clarity, 3 carbons and 8 hydrogens as my reactant there is the formula for propane. So I'm going to use the word propane just so I'm not rhyming off the chemical formula all the time. But the combustion of propane, and you look at the balancing numbers. Now, if arbitrarily picking a number for propane being consumed at, say, 2 moles per liter per second, which is actually really, really rapid, so it probably is not very realistic. That would mean that oxygen is being consumed 5 times faster, because for every 1 propane I need 5 oxygens. It would also mean that carbon dioxide is being produced at 3 times that speed, because for every 1 propane I get 3 carbon dioxides, and a similar story for water. So the rate of each thing is going to be unique to it, but they're all going to be related to each other through the balanced chemical reaction. And you might be wondering, is it always that easy, or does that always work? Maybe you didn't think easy, but maybe you wondered if it was always worked. And the answer is yeah, stoichiometry. So if I take a specific example here, where I've got nitrogen, hydrogen reacting to form NH3, which is ammonia. If I pick let's say maybe a more realistic number for a rate of 0.005 moles per liter per second in terms of production of ammonia, if I wanted to know the rate of consumption of nitrogen in this case, then I could set up a formula something like this. Not really a formula, but I could set up a relationship something like this, where I take the rate with respect to ammonia, NH3, and I multiply by the balancing coefficients as I would do if I were doing stoichiometry. Now, you might not have set up your stoichiometry this way, but that's really what I'm doing, is I'm looking at least one step of stoichiometry, comparing moles per liter of one thing to moles per liter of the other through the balanced chemical reaction. And that would give me, unsurprisingly, a number of 0.0025 moles per liter per second for the consumption of nitrogen. Now, the same would be true for hydrogen. Well, not quite the same. It would be the same process, but not the same number. There, I would be multiplying by the balancing coefficients for ammonia and hydrogen, or hydrogen on top, ammonia on the bottom, 3/2, which would give me 0.0075 moles per liter per second. So this is something that we're going to be doing from time to time. Now, you might wonder why we need to do that. And the answer is that I need to often report, or I'm interested in the rate with respect to one particular thing, but it might not always be the thing that I'm measuring. So for example, if I were, well, let me give you an example here. If I had this example, and I'm not going to go through and say what this stuff is, but if I look at one of the products, this middle product there, I have H+. You may remember from acid-base chemistry that H+ is the thing that makes an acid an acid. So within that reaction, I could probably fairly easily measure the amount of H+. I could measure pH, and I could relate that to concentration of H+, hydrogen ion. But I might not actually care about hydrogen ion. I might want to report that rate in terms of the more important product, the first product, or perhaps the more important reactant, the big reactant there. I might want to know the rate with respect to those things because they look big and important, but I might not be able to measure them easily. Now, in this case, all the reactants are 1 mole reacts with 1 mole that produce 1 mole. But if I combine this idea with the previous one, then being able to convert the rate of one to the rate of something else becomes actually fairly important. And I just said that. Okay, a couple of other things before we wrap it up. Number one is, in terms of the mathematics of it, if you look at the slope of the reactants, they're going to be decreasing. So the slope is going to be going down. It's going to be a negative number. The products are going to be coming up. Now, I didn't pay attention to any of that in those previous calculations, and we generally don't need to, because as long as we report what it is that we are measuring, what it is that we're reporting, and we use words like consumed or produced, then it will be clear what's going on. So often cases, the mathematical negative number that we get just tells us it's a reactant going down or decreasing compared to a product that is increasing. So then algebraic signs are going to mean less. One of the challenges that we'll have, and it's going to be a particular challenge for us with being in a high school is how do you actually measure concentration of something quickly and accurately? There's a couple of options, but we're pretty limited. So we're going to have to do a couple of things that are a little bit off script compared to what we've been talking about in the last few minutes. And one other thing is that because the rate can change depending on conditions, and we'll look at what those conditions are and how they influence the rate, and we'll look at why they influence the rate a little bit later. But because those conditions can influence the rate, I often need to state what the conditions are. I only say that because you're going to see a lot of questions where it tells you a temperature, that the rate of something, something, something at 400 degrees is, you might not ever use that 400 degrees. It's just telling you the conditions, because the conditions change, the rate changes. Okay, right now at this point, and I know we haven't done a lot of practice, but sort of at the end of our next step, you should be able to take the rate I'm getting ahead of myself here, come up with a rate given the concentration changes over time. So changing concentration over time, come up with a rate, okay? Concentration 1, concentration 2, time 1, time 2, simple math. You should also be able to convert the rate of one thing, one substance, one product or reactant, and convert that into the rate with respect to another thing, kind of like what we were seeing before. And then some of these other bits and pieces, they're gonna kind of fall out into our lap, or we're gonna deal with them specifically on their own. Anyway, that's an introduction to rates. We'll talk to you another time.